So thank you so much for having me. I'm really excited. I have not done a seminar like this at Davis before. As he mentioned, I'm Corinne Scown. I'm a senior scientist at Berkeley Lab. I have a joint appointment at UC Berkeley, so I kind of maintain groups both places, and they sort of float in between and have joint appointments and whatever. And my specialty is technoeconomic analysis and life cycle assessment. And I mostly work on, historically, like bioenergy, bioproducts, and then my research portfolio has kind of morphed to the point where I'm also doing carbon dioxide removal, CDR, because a lot of that has a kind of bio element to it, so the skills translated. And then some of the collaborations that we've had have been kind of on transportation electrification, which has always just been like a sort of low-key thing that I like to do because it's super fun. I'll go ahead and get started. I'm going to talk mostly about some of the sort of efforts to become carbon negative. And I'll give you some context on like the motivation for that, and then some kind of vignettes of like projects we're doing. My background, I'm an engineer by training. I did my graduate work at UC Berkeley. I did my undergrad at Carnegie Mellon. I am also a startup co-founder for a biomaterials company, so that's like conflict of interest disclosure. It's a very like specific, like novel polymer, so we're really not going to touch on that stuff today. But you know, just full disclosure. And then right now I'm actually spending half of my time on detail to the Department of Energy as a senior advisor for clean fuels, and I'm specifically working on implementation of tax credits in the Inflation Reduction Act. So all things related to transportation fuels and a few non-transportation things. So what's kind of this vision for like pulling carbon out of the air? We know we need to decarbonize, and that is the priority, right? We've got to mitigate emissions from the sectors that are sort of the main contributors to anthropogenic greenhouse gas emissions. But we also recognize that some of that mitigation is going to be so expensive that there will be other alternatives for like pulling CO2 out of the air that might be cheaper or at least more practical to scale. And we also know that in order to kind of reach climate stabilization, we need to be able to pull CO2 out of the air. And so this has spurred like a whole new market, which I didn't know as much about, I'd say even like 3 or so years ago. But I have come to appreciate that CDR has sort of started to displace like carbon offsets, and it has become the thing that companies want to buy to reach their greenhouse gas goals. So they can't effectively mitigate all of their emissions. Carbon offsets are kind of getting like a bad rap, because how do you prove that some emissions would have happened and that you paying for something has caused them not to happen? That's like many opportunities for sort of gaming that and saying you were going to emit more than you really are. And so they've said, well, you know, we trust systems that we can like show physically are pulling CO2 out of the air. Like nobody can argue with that, so that's what we're going to buy. And that has spurred this interest in carbon negative technologies. So this is just like one example of kind of what this can look like. So there are different ways you can pull CO2 out of the air, but one of the ways you could do it is just having plants do what they do, right? They're gonna take CO2 out of the air, they're gonna fix it in a stable form, and you can do stuff with it. You can convert it into long-lived products. So this is one of the collaborations we have with Sabby Miller here is on building materials, sort of carbon storing building materials. You can also convert it into energy products that are not long-lived, but you get CO2 or something else like biochar, whatever, as a byproduct, and you can sequester that. And then you get some of that CO2 that came out of the air in a stable form, and you can store it. And so depending on how the emissions kind of balance out in that system, you can theoretically be sort of net pulling CO2 out of the air and putting it someplace stable. So if we were going to do this, there's a few different ways to make it work. I mean, the first is just like focus on the carbon storage part of it. We're not going to try to get anything else valuable. If we get something valuable out of it, great. We'll take credit for that. But in general, you're just trying to get as much of that plant biomass into some kind of stable form and put it underground. And so, you know, one option is to, the conventional one, the one that is selling the most right now, is to do slow pyrolysis on your biomass, make biochar. And right now, there's sort of, some people are applying it to agricultural fields as a soil amendment. Some people are trying to put it underground in some form. You can bury it. But that's probably the most like expeditious way to get that carbon in a somewhat stable form and put it somewhere. You can pyrolyze, do fast pyrolysis, and get a bio-oil, which is like terrible as a like, it's awful to handle, it's corrosive. It's kind of a nightmare to turn into fuels, but it is pumpable. And so at that point, you could pump it underground. This has led to a bunch of companies that say, we just got to get something pumpable, guys, like bio-oil, or how about we just make something that is kind of a solid and then we turn it into a slurry and we pump that. Well, you know, once you have something that's kind of, that's liquid enough, you can pump it underground. And then the only question really is like, how well sealed up and monitored does that underground formation need to be to guarantee that whatever you put underground isn't like breaking down and re-emitting things like methane? Open questions, right? Still figuring this out, yeah.
Or polluting water?
Yeah, also that. Many open questions. And one of the challenges is, for better or worse, startups in this space have been very creative in coming up with different ways to try to get carbon underground. And there isn't like a regulatory body that is resourced and tasked with like figuring out how well these things work. And so it is the companies that are trying to build their own, we call MRV, measurement, reporting, and verification frameworks. They are trying to test the stability of their own systems and then report that and use that to try and convince people to buy these carbon credits. And sometimes, often, companies will pay in advance for carbon storage that has not yet happened because, of course, you got to have the money to, before you can spend it and do the thing. So, yeah, that's option one, putting as much carbon into the ground as possible. Lots of pitfalls there. Obviously, conflict of interest when the companies are sort of self-regulating. Like, I think in many cases that doesn't work out so great. Okay, the other option is try to get as much value out of this organic material as you can. Use it to mitigate emissions for the sort of difficult to mitigate sectors like aviation. And then you can kind of integrate carbon removal into that to the extent that you can. So, you know, we do work on CDR, but one of the questions we wrestle with is also like from the perspective of a resource. Like you can ask this question of like, I have this resource, what's the best thing to do with it? And that is like an ongoing debate. And there are people who feel really strongly on both sides. But you know, there's an acknowledgement that aviation fuels, it's one of those things where it's possible that biofuels might be the only viable option in the near term. I'm sure some of you disagree on that, at least for some kinds of aviation. So yeah, in terms of the like role of biotech in climate change mitigation, there's two truths exist, especially in California. We have too much biomass, like organic residues, whatever, and we've got to figure out something to do with them. You know, we're landfilling waste. Farmers are not allowed to burn off their like orchard trimmings anymore, and so they're just chipping it and like piling it up on their fields, and it's causing all kinds of problems. And then there is the other perspective, which is that we have so many needs for this stuff, and we don't have nearly the amount of biomass that we need to meet all of these needs, and like it's a huge problem. And really, anytime you build out this industry, you're just going to cause all kinds of knock-on effects. You know, land use change, you will drive up the price for these things that actually were useful as animal feed. And I have heard, like, we just had a sort of closed-door meeting with some California, a bunch of California agencies who are all interested in, like, land-based carbon management. And somebody just laid this out. She was like, I have heard these two arguments made at the same time, and I don't know which of them is true. But there are things we can do, right? We can make technological advancements to both make it easier and cheaper to do carbon removal, especially in places where you can't get like economies of scale for some of the more high-tech conversion industries. And we can focus on developing better technologies that convert the stuff that is sort of accessible enough and easy to convert into like the fuels that we need, replacements for petrochemicals, et cetera. So these are the vignettes that we're going to talk about today, and we can sort of emphasize or de-emphasize these based on your interests. So one I'll talk about, and this is happening now, is the integration of carbon capture and sequestration into biorefineries to start taking some of that biogenic CO2 and putting it underground. We'll talk about processing organic waste to make sort of a range of products, this like vision of like take the biomass and then kind of extract as much value as you can out of it. We will talk about a real world example, Zero Waste Energy Development Company in San Jose, and the like I think it was 4-year project that we did with them, understanding their economics, their environmental impacts, and kind of what that means for like California's plan to meet SB 1383, right? We got to divert a lot of organic waste, and there are some upsides to that, but also some real challenges. And then we'll talk about kind of national scale considerations for CDR, particularly with an eye towards like biomass reliant strategies. Okay, so this is like an older study now. It came out in 2020, but we were interested to see what would happen if you integrated carbon capture and sequestration of various flavors into a conventional ethanol production facility. I say conventional. We analyzed like a lignocellulosic facility, which I realize is very much like not the status quo right now. It's corn for the most part, but we want to see like does it pay off? Like how expensive is it? And so since we published this, like this is happening now, and there's a couple of different ways you can do it. So these facilities they produce two different CO2 streams. There's CO2 off the fermenter. So when you ferment sugars to ethanol, it's an anaerobic process, and you get a relatively pure CO2 stream that's like requires like really minimal treatment before you can compress it and put it underground. In fact, they already use that CO2 stream. Some of them sell it to food and beverage manufacturers, so it's not even necessarily wasted. And then you have what is much more expensive and less fun to deal with, and that is the post-combustion CO2. So you burn natural gas, you can capture the CO2 in that flue gas, and then you can compress that and put it underground as well. So like do the economics like pencil out for one or both of these, and what if you start incorporating policy incentives? Kind of how does that work? And so we built process models for each of these. And this was like sorghum biomass, just as a case study, but it wouldn't change that much either, even if you swapped in some other kind of like crop residue. So we looked at sort of what this looks like without policy incentives. Obviously, there is no like market value to putting CO2 underground, right? So it is not surprising that it just increases your costs, and like why would you do it? Best case scenario, it's a waste stream and you're not losing any revenue. Worst case scenario, you used to sell it and now you're going to put it underground. You get no money for it. You have to pay to put it underground. Then you factor in RIN credits, so Renewable Fuel Standard. It doesn't have that close tie with like the carbon intensity of your fuel, right? So it really just depends what bin you fall into in terms of the category of RINs, D2, D3, et cetera. So this is like a really interesting thing that I have learned. Yeah?
What is RIN?
Renewable Identification Number, RIN, and it's basically tied to like gallons of ethanol equivalent on a lower heating value basis, I believe, that get blended in with transportation fuel. And so they have these like volume targets, And blenders meet those either by sort of paying somebody else who's blending more than they need to, or purchasing biofuels. And there are like targets for different categories of RINs. People can correct me if I'm wrong. I'm sure there's somebody who knows this market better than I do. But like the different categories of RINs correspond to different types of fuels, and they have sort of greenhouse gas intensity thresholds associated with them. So the higher value ones have a sort of higher bar for like greenhouse gas emissions reductions. So you can think about like, you know, a hypothetical like corn stover to ethanol facility is going to get a higher value per gallon of fuel that they produce than like a conventional like corn ethanol facility. Does that make sense?
Is that because of its like carbon?
It's the greenhouse gas intensity.
Or like reuse potential?
It's the overall like greenhouse gas intensity of the fuels, or the carbon intensity, the sort of CI score, so to speak. So like you do the full life cycle assessment, you assign like X grams of CO2 equivalent per megajoule of fuel, and that is the fuel's carbon intensity score. And they have, each RIN category has like a threshold, like you have to reduce greenhouse gas emissions by more than 50% or more than 60% to like fall into a particular bucket. They also have requirements for what kinds of feedstocks are eligible in those different categories. So RFS is interesting, but yeah, that's kind of what it comes down to. So basically, your sort of optimal scenario, if we go back to S2 here, is to not do CCS. These facilities co-produce some biogas, and so if you upgrade that to like renewable natural gas and sell it as a transportation fuel, you get some credit for that. And so that's your optimal scenario, is don't do any CCS. But if you incorporate the California Low Carbon Fuel Standard and you're selling in there, suddenly do as much as you can. You should do as much CCS as you possibly can. And I honestly think the only limiting factor here is just the pace at which people are getting Class 6 permits and setting up the necessary infrastructure to do CCS. But this is where I see the industry going. What has changed since we did this study is that even corn ethanol facilities are also selling this biogenic CO2 injection into the ground as carbon dioxide removal, which is interesting because they are taking a facility that, like, on a life cycle basis is still a net emitter. If you built more of these, you would be contributing to greenhouse gas emissions. You might be like potentially reducing it relative to gasoline, but like the whole system is not like net removing CO2 from the atmosphere. But because they point to the fact that the CO2 from the fermenter came from biomass, they are saying we're doing CDR. How do people feel about that? I'm actually really curious. Like, does that, I guess, raise your hand if that feels like a good thing. Like, yeah, fair enough. Like, that's CDR. That's okay. Like, raise your hand. Yeah. Yeah.
So why wouldn't that just get embedded in the CI number so that they'd have a lower CI number? That seems like the net calculation we should look at.
Yeah. So great question. So there is like a whole separate question, which I think is still muddy even to some of the regulators, on like when claiming something in like policy incentives means you are transferring the environmental attributes and you can't claim it somewhere else, and when you are not. So like what things can you stack and what can't you stack? It turned, like, I thought it was confusing, and I thought that maybe when I started doing my detail with DOE that everybody else would know the answer to this, and it turns out they also don't. But yeah, so that's one thing. But I agree. So like the other alternative, you can imagine a scenario in which they took the exact same amount of CO2 and they captured it from combustion of fossil natural gas, and they put that underground. Atmosphere doesn't care. It's the exact same system from the atmosphere's perspective. They would not be able to sell that as CDR because it was fossil CO2.
Wait, what? Why not?
Because in carbon markets, they want to look as narrowly as possible. I say they, like companies that are claiming this, and some of the protocols that are sort of facilitating them claiming this and selling these as carbon credits. they will take this very narrow view and say, these molecules of CO2 were in the atmosphere, the plant took them up, we are then putting them underground, ergo, we are doing CDR. Yeah. So that's where things are, like, you guys, you should get involved in this, because it's like a whole growing industry and they need people who understand emissions accounting in these systems. So there, yeah.
But I guess would the argument then be that since they're taking fossil carbon and then just not emitting it and storing it long term, that it's not removal, it's just avoiding emissions. So that's the main difference, is that at least by using a bio source, it's at least pulling CO2 that was in the atmosphere at one point.
Yeah. So I think if you could try to make a logical argument here, you could say, well, if I decarbonized everything else, as I would in some future decarbonized situation, then this system really would be doing CDR. So it has the potential to do CDR in the long run if I mitigated all of the other emissions.
Can you say, in the short amount of time between me combusting the fossil fuel and capturing it, it's technically in the air?
In fact, we had this discussion. So I work a lot with the folks at Lawrence Livermore Lab who've been like kind of in CDR for a little bit longer than I have. And somebody was saying like, well, we need to make sure that we don't allow for people to like do like direct air capture, but situate their plant right next to a source of emissions. So they're like sucking out like a concentrated stream that someone just emitted and claiming it as CDR. I know, I'm like, actually, that's not a bad idea. You should go to like wherever their like fugitive methane emissions are and just suck those out of the air. Like, why let it dilute?
Exactly.
Yeah, so anyway, more to come on that. But if you are curious about this, there's an organization called Carbon Plan that wrote like an article that was specifically like CO2, like CCS at ethanol facilities is not CDR. They wrote this blog post and it's like made a lot of people angry, obviously, because people are trying to sell this stuff. But we published an article in One Earth like a week or two ago that effectively said the same thing. That like that's mitigation. Like, congratulations, thank you for mitigating. You are not doing CDR. But yeah, there's a lot of, happy to talk more on that because it gets really, really wonky. Another contentious issue, manure digesters. And this is another study we published back in 2023, but I'll kind of sprinkle in some slightly newer anecdotes here. So the idea is basically, if you're going to build these biorefineries, you will often have like a lot of wastewater to treat. And so you'll do on-site wastewater treatment. For the corn ethanol facilities, I've gotten kind of like somewhat cagey answers when I ask about their wastewater treatment situation. And what I have deduced, I think, is they do like the bare minimum, obviously, to meet regulations, no surprise there. But because there's not a lot of like nasty solvents and stuff in there, sometimes they'll just try to get rid of it by like spraying it on animal feed. It's got like sugars in it, and they'll say like, it's calories, just spray it on the animal feed and feed it to the animals and it's fine. And we don't have to like have like an aerobic or anaerobic digester. But at these more advanced facilities, they convert biomass into stuff. You're gonna have some things in there that you can't feed to animals. Like you're gonna have to have a wastewater treatment plant. We've always modeled it this way. Now, the solids loading in those wastewater treatment plants is often like not that high. Like commonly, like at wastewater treatment plants in general, if you have an anaerobic digester and you've got room to add some additional solids, you have this possibility for co-digestion where you can take in any kind of like high strength organic waste, some of which may have gone to landfill or like septage treatment, and you can co-digest it along with your wastewater, get some extra biogas out. And then you can use that as energy. You can either burn it on site for electricity and heat. You don't have to, you have to sort of treat it and remove some of the impurities, but other than that, it's fine. Or you can upgrade it to renewable natural gas, and you can use that in place of compressed natural gas, either in vehicles or you can inject it into the pipeline. So we were kind of curious, like, well, why don't they do that? Like, there's a bunch of biorefineries that we're like envisioning building in the Midwest, or have all these second generation, whatever, like just to take in some extra organic waste that's around you. In these rural areas, there should be a fair amount of manure. And in theory, you could get like pretty decent benefits on your greenhouse gas intensity if you did that. So we ran some scenarios, and I know it's a lot of text here, but like basically, we partnered up with, so we like, you know, we wanted to understand what this kind of co-digestion situation was going to do. Would this be like good for facilities? And we were also kind of talking to companies and figuring out if anybody was actually thinking about doing this. And it turns out they were, except that manure is so valuable in California for just like regular dairy digesters that it was too expensive for them to procure. But we looked at a few different ways that you could increase your biogas generation and then use that biogas, okay? So the biogas, about 50-50 mixture of carbon dioxide and methane, and then you've got some like ammonia, you've got H2S in there. You have to sort of get that stuff cleaned up. Like you have to clean that stuff up at least. And then you could just burn it on site. I mean, that's what a lot of like older facilities with digesters do now. You just burn it as a fuel. You can do heat and electricity generation. You can pre-treat it and then upgrade it, remove the CO2, you get compressed biomethane. You can sell that as a transportation fuel. You could use it for your own fleet if you're going to be like hauling feedstock back and forth, hauling fuel out. The other thing you could do, and this was a partnership with Mango Materials. So they're building facilities that do microbial production of polyhydroxybutyrate, so a compostable plastic. And they're also looking at single-cell proteins. And so there's yeah.
So what's the benefit then of turning it into fuel if you're just going to burn it again?
Well, you definitely get more energy out than you have to put in to do the conversion, right? Like you're taking this organic waste that would have presumably been either landfilled or would be going to some like basically negative value application, right? Like somebody's like paying to dispose of it. And you're going to, you can't, it's too like wet to just like burn it. But if you put it in an anaerobic digester, you can get like 50% mass reduction. Like half of that mass goes away and you end up with a usable fuel. So you don't have to use as much natural gas if you've got extra biogas on site. You can even be a net exporter of electricity. Does that make sense?
So it's still like a high carbon fuel.
Yes, but it is biogenic carbon. So in theory, it's kind of part of a closed loop. Yes. Yeah. So those are the options. And Mango Materials is doing this. They're largely looking at like bolt-ons for at wastewater treatment plants. But that's effectively what this ends up being in these scenarios. So, like, how do the economics work out here? This represents a long-term shift that we are seeing, like, at any anaerobic digester, which is producing, we say bio-CNG, but whatever, people call it RNG, renewable natural gas, is like generally the more profitable thing to do. And so that actually beats out the conventional case, which is this is like the standard, like NREL's been like publishing the same scenario forever. And we basically proved that if you do this, like you can get lower costs than the kind of standard NREL technoeconomic analysis case, which is heartening. You know, you increase the renewable fuel production, the economics kind of work out, even without policy incentives factored in. The greenhouse gas case, if you are able to not use petroleum diesel and instead use RNG for like your on-site fleet, for example, that's really, really useful. You get less of a benefit if you're going to inject it in the pipelines because then you're offsetting natural gas, which is less carbon intensive than petroleum diesel. But yeah, like in general, that scenario like won out. Producing PHP and SCP, you know, I have noticed that for all of the lip service we give, like bioproducts, like, oh, we gotta have renewable alternatives to all these petrochemicals that we make. And then single cell protein, obviously, is like an animal feed. Neither of those markets have any policy support, meaningful policy support. And so I do not see them happening. Like, they have to compete with like pretty cheap commodity products. There's a ton of policy support for like fuels, energy carriers, but you know, parts of the federal government have invested really heavily in producing like bioproducts, but those things it is an uphill battle for them to compete with the conventional petrochemicals, and I just do not see the policy support to sort of flip that equation and make it work. I am curious if anybody else knows differently, but like, I don't know. It's like, we either have to like put a value on some of the reduced externalities here, or like it's probably not going to work. Not to say anything bad about mangrove materials. You know, they're doing fine. They live to fight another day for sure. So yeah, in terms of the cost of CO2 mitigation, so if you factor in like the additional cost for like gallon of fuel that you produce, and then sort of work out like how much you're paying per ton of CO2 that you mitigate across the system, the renewable natural gas case, or as we call it, bio-CNG, wins out again. Like about $67 a ton. Man, that is cheap. The social cost of carbon, established by the EPA somewhat recently, maybe last like couple of years, that came out. What is it, 195-ish?
That's the new one.
Yeah, the new one. $195. I know, Max worked on that. $195 a ton. We just asked him to tell us how to do the calculation. It's really hard to figure out like doing discount rates and stuff with these things that happen in the future. But yeah, $195 a ton is kind of like what we say we should be willing to pay for greenhouse gas emissions mitigation. And so $67 a ton is like, that's a bargain. Most of these things, in fact, all of the alternative scenarios work out to be less than that. And one thing I have found super interesting is if you go into the Inflation Reduction Act and you just pull out some of these policies, and like, it's not like they say, we used the social cost of carbon and we kind of like worked backwards and this is why the dollar values are what they are. For a lot of these things that I've worked on, if you back engineer what they value for the social cost of carbon, it never turns out to be like exactly the EPA number, but it's often like pretty close. So I think that's super interesting. So you guys should all include social cost of carbon in your like papers and stuff. It's great. Yeah, the other thing that really makes a difference is if you're taking in organic waste, there is more uncertainty in like the dollar value or cost of that waste than like most other things, right? Like, am I getting paid to take it, or am I paying somebody to give it to me? And that answer can depend on, first of all, what kind of waste it is, like how contaminated it is, what other markets they have. Could they have fed it to animals? Could they have used it as, if it's a dry thing, like animal bedding? But it also matters like how far they have to transport it. And so one of the things we ran into with the roadster removal report with Livermore is that we would have these scenarios where waste had a positive value in population dense areas where there might be like more options for using it and you don't have to transport it as far, and there's better source separation because you could do that in urban areas. But then in like rural areas, the waste would have a negative value. Maybe I got that backwards. Negative value in the urban areas, positive value in the rural areas. Yeah, so it truly depends on like what else would you have done with this stuff if you weren't delivering it to the facility. So the transition here is we've looked at PHB, like a bioplastic, and around this time, 2023-ish, people started publishing all these papers that were claiming that they had bioprocesses that were carbon negative. And the reason they were doing this is basically they would draw the system boundaries, like that didn't include whatever their product was going to get like used for. And they would say, well, I'm making a product, I'm making a solvent, I'm making a plastic, whatever. It's not made to be burned. Therefore, I am taking atmospheric carbon and I am putting it in a stable form, and don't ask me how people use it later. It's sequestered. Like, this is a carbon negative process. I reviewed a paper that said exactly that. I reviewed many papers that say exactly that. And so I started getting really curious because it was driving me crazy, like all these papers. And they would never do the like scale calculation. They never say like, does this actually matter for the climate? It would just be like, my process like net removes carbon, and don't ask me how big this market is, or also what people are going to do with my product after they use it. And so I kind of wrote this paper that basically went through all of these different products that could be made via sort of biotech, right? Everything from like solvents to biopolymers, et cetera. And first of all, just knocked a bunch of those out. We're like, solvents often get oxidized at their end of life, or they go to wastewater treatment where they are also oxidized. Like you're either burning it or you're sending it to wastewater treatment. So don't tell me your solvent is like sequestering carbon. It's not. Best case scenario, if you make a plastic, or best case, but like, and then it gets landfilled, I guess you are kind of sequestering carbon. You put it in a state, it's very stable. Unfortunately, you dispose of it, it probably will not come back out. And so then the question was like, how big of a deal is that? Like, is plastic, like, is that a good like carbon sequestration strategy? And are landfills really like how we want to be doing carbon sequestration? And so I just did the math on this, and basically, even if we landfill like 90% of our plastics, I think these are global values, it is like a drop in the bucket in terms of like the greenhouse gas balance. Like, this is a really, really stupid, expensive way to try and sequester carbon. So don't let anybody tell you they got their carbon negative plastic. Just be like, yeah, whatever. Since then, we've gone a step farther and said, here's the thing. Like, if you build a whole system that is designed for all of our waste to be landfilled, even if your plastic is not breaking down to methane in the landfill, the fact that we're sort of producing and using all of these plastics and they are contaminating a waste stream that does cause net emissions at landfills, like your plastic, if it's not designed to be easily recycled, is really just part of the problem, and it is a contributor to the emissions that we experience from landfills generally. Yeah?
If the plastic is stable, then how is it contributing, even if it's in a landfill?
Well, so this gets into a little bit of like, yeah, fair enough. Like, your film plastic that you like ball up and throw away is not breaking down to methane. However, all of the efforts to divert organic waste are hindered by the additional costs and technical complexities that are contributed by the presence of plastic contamination in organic waste. So like, composting facilities have to buy these freaking depackaging machines that screen out all of the plastics. Facilities that like want to compost their like solid digestate have a difficult time finding any like reasonable takers because they have an incredible amount of plastic contamination. I'm going to show you pictures in a second. And so that stuff gets used as like alternative daily cover in landfills. Now California is like banning this, so I don't know. Well, you'll see why I think this is crazy. Okay, so this is a real facility. We did a big, long project funded by the California Energy Commission with this facility in San Jose. We basically got to like learn alongside it. Was at the time the largest high solids, they say dry, but it's not really dry, high solids anaerobic digestion facility in the world. And they're taking in like food waste that you would throw away at restaurants. San Jose has a bizarre source separation system called wet and dry bin. And so you, yeah, I know. And so it's basically like all of the like uneaten French fries and whatever, and like the, you know, clamshell packages and stuff. Like you, like if it's like paper, you would put that in this wet bin, and that would end up at ZWED. They also took waste from Palo Alto, including the Stanford campus, a bunch of the other like company like office parks over there, and yard waste. They had a few different sources, but the big one was like San Jose, like restaurants and also direct haul from grocery stores. So sometimes they get these hauls that were full of like rejected or spoiled food, like produce and stuff. And so what they would do is bring this stuff in. So a combination of green waste, municipal waste, and manure, ideally mostly organics. They would do sorting and processing, try to screen out the recyclables and send those to a recycling facility. They would then try to squeeze out as much water as they possibly could because they're going to load it in their quote-unquote dry anaerobic digestion system. It's still like 70% water, but it's like a pile as opposed to like a tank full of water. And they shove this waste into what looks like big shipping containers. And they shut the door. And then it is a batch process, goes for about a month. There is a system that sort of sprays inoculum, like water with like microbes and stuff to kind of get things cooking in there. It sort of recirculates that over the period of the batch. Microbes get to work. They are breaking it down into biogas. That biogas is then used for electricity generation and heat on site, including providing some heat to the digesters. So they like thermophilic process. They like to be hot. And then when it's all done, they have to take whatever's left, the like solids, and they got to do something with them. They want to send it to compost, but they have to screen out a lot of contamination. And they also like to, again, squeeze out as much water as possible because they all pay per ton. So like a constant theme was like, get the water out so we don't have to pay somebody for it. And then, yeah, they've got these CHP units on site, 1.6 megawatts capacity, not that big. And you can see where they are, right there, San Jose, like right on the bay. So we won't go through the crazy process details, but like basically we spent a lot of time mapping out this facility. We had access to their like online system that they would use to actually control the facility. So it was terrifying because I'd go in to pull data and like I had the ability to turn the flare on and off, which I was like, don't click the wrong button. Yeah, they also have a lot of systems. Like one of the things I appreciated about this is like, just how many different sort of sources of like contaminated enough like air that they couldn't just release. They had to treat it. So like in the receiving area for the waste, it's stinky, it's starting to break down even though they can only keep the waste for like 48 hours. And so all of that stuff, it has to be under negative pressure and then they route it through these giant area. These are wood chips. They put it through these biofilters where they cultivate a film of microbes on the wood chips and they sprinkle them with water. They have little they look like drip irrigation lines. And then this air slowly goes through. And by the time it comes out, it smells like nothing. It's like actually incredible because it is vomit inducing in the receiving hall. And by the time it comes out, I was very impressed. And they eat the methane as well. The methane concentrations are really low when they come out there. Yeah. The other thing I appreciated is just how hard it is to run a batch process. So you think about like, you put the waste in, you got to start up this digester. It takes a while for the microbes to really get cranking. And so for a while you're getting pretty lame biogas. It's like not a lot of methane in there, but it's also like too high for you to just emit it, but it's not, the methane concentration isn't high enough for it to ignite either. So like what the heck do you do with that? Well, you take some rich biogas that ideally you would like to use for electricity generation and you have to supplement your lean gas so it has enough methane to ignite so you can burn it all off because otherwise you're just emitting it to the air. Livestock facilities don't have to do any of this. They just like, no problem, just straight into the atmosphere. But these facilities are pretty regulated. Yeah, so waste, like about half of the mass is remaining at the end of the process. So you lose like half of the mass actually gets broken down into gaseous products.
A lot of that is water.
This is just the solids.
Oh, okay.
Yeah. Doesn't include the water, because I know the water is like a complicated thing with all the extruders. Okay, so this is what one of the digesters looks like, where you could see the big door swung open. Yeah? Mm-hmm.
How much of the methane is flared off? It seems like a not great, you know?
It's better than
It's better than
I guess
you.
it's better than just like emitting it, but
Yeah.
is there another option? Something like, I mean, you're collecting all this methane, do something with it.
Well, they don't have an upgrading system, and they didn't have access to a gas pipeline. This is actually a landfill redevelopment project, so they sat on top of a landfill. In fact, they had some settling issues. But they didn't have, it would have been more lucrative for them to do like gas upgrading. I don't know how well those systems do with some of the leaner gas streams. You probably still would have had to flare off a decent amount. But this is, yeah, it's just a challenge. Now, any of these companies that talk about doing like atmospheric methane removal, I'm like, why don't you start with these streams that have way more methane in them than like atmospheric concentration? So this gets back to like this like CDR market causing like weird incentives to like pull things out of the air when you could very easily go take like low-hanging fruit. But yeah, it's I take your point. It feels like a waste, right? How much got flared? Probably like 15-20%. I mean, it's like not insignificant. It's a lot. Okay, so that's what one of the digesters looks like. They had, I think, 16 of them. This is the combined heat and power facility. So they were burning the biogas after it's been treated. They have a heat exchanger. Only one of them is connected to the heat exchanger, and then they heat the digesters. They're thermophilic. Another challenge with biogas, this is a storage bladder, and then you can see the people for scale. You can't like compress biogas and store it in like those nice little round storage tanks that you see for like natural gas. You have to store it at atmospheric pressure. And so that means they have 2 big bladders on their roof. That stores like maybe 2 to 3 hours of production. So like the notion that any of these facilities can like do, you know, provide grid services or do like load following or something, like I don't think so.
They can't compress it.
You have to upgrade it to compress it. Yeah. Also, tons and tons of contamination. So this is like, you know, when we have these like zero waste goals, I feel so bad for these facilities that have to make it work because they are really dealing with a lot of awful waste streams. So this is what it looks like pre-digestion. Look at the amount of plastic in there. It's wild. They did have a price structure where they could get paid more depending on the level of contamination. So they actually made out better with the highly contaminated waste streams than they did with the cleaner waste streams, even though they complained endlessly to us about the contamination. But yeah, they would get stuff like this, and then this is what it looked like post-digestion. It's like dark, turns like a dark, dark brown color. This is the compost facility in Gilroy where they were hauling their stuff. And their material was so gross that it got contained in ag bags. So you see the white ag bags? That's how you know it came from ZWED. All the other stuff is like nice, like yard trimmings, it smells pretty okay, you know, but not the ZWED stuff. I had a colleague who was we wanted to understand the emissions from like soup to nuts, right? They were doing measurements in addition to all of this modeling. And so she was out there doing emission measurements for the composting operations. And she said the leachate would come out. There'd be like residual water that gets kind of squeezed out over time. And so you have this like stinky garbage water that you're like mucking around in. And then the occasional rat would like run by. See, California Energy Commission would not pay for travel. So they had to get up like at the crack of dawn, drive down. They wouldn't pay for a hotel. Like drive to Gilroy and go take these measurements. It did not sound like fun, but we soldiered on. She soldiered on. I didn't do the measurements. Okay, so get into the actual. This is a paper. There's like several papers from this project, but I'm going to talk about the one that came out of my group because I'm here. We were curious, like first of all, like how does this work out relative to landfilling? Like, is this better? I mean, now we have like measured the heck out of this facility. We know like ambient concentrations of methane. We can kind of figure, they did like measurements at the flare, measurements at the biofilters, like every possible point that methane could have been escaping, like we got it. They were doing measurements for air pollutant emissions, so we could do social cost of air pollutants and really get a handle on like how does this work out if this is like the future of what we have to do with our waste and not landfill it here in California and other places too. Okay, and did the high tipping fees make sense? They get guaranteed higher tipping fees, about double what you would pay to landfill it. Okay, so it's like $100 a ton. Is that like worth it? Like should they be, are we getting like social benefits that are commensurate with the extra money that we're paying? And then were there better things they could have done? So we get it, like they don't have a gas pipeline access. But if they did, would that have been better? Okay, so scenarios here. Landfill the waste. Just send it to landfill. Like that's what it's going to look like. And this is greenhouse gas emissions. I'll get to the air pollutant stuff and social cost in a second. How about just compost it? Compost waste. You got to screen out a lot of contamination, but you could compost it. Okay, this next one is like do basically what they're doing except landfill the digestate. Okay, this one here, do basically what ZWED's doing, but land apply the digestate, just spread it on land. Some people do it without even composting it. These two are basically the same as the last two, but you're going to compost the digestate. Okay, so instead of just taking the raw digestate and spreading it on the land, you'll compost it, which is what they do. They send it to a composting facility, and then these last two are upgrade the biogas to RNG. So don't burn it for electricity, but instead make RNG and use it as a transportation fuel. Okay. Oh my gosh, I keep getting the Wi-Fi pop-up. So fugitive methane emissions from landfills. Like this is why SB 1383, that's focused on methane emissions reductions, has all this stuff in there about diverting organic waste. This is actually quite a bit lower than what the EPA WARM model says. EPA WARM model gives you about double this value. But we had some concerns about what those values were and got some really good constructive reviewer feedback. So this is kind of where we landed, and people seem to be coalescing around a value about like this. But it basically says like do literally anything else but landfill this stuff. It really is quite bad. And this factors in like landfill gas collection and flaring, but there's still quite a bit of fugitive methane emissions that are not collected and flared. Okay. So then if we're going to do anything else, you know, composting looks pretty okay from a greenhouse gas standpoint. I mean, you don't have to do a lot. You know, you have to aerate it, you turn it, or you can do like positive or negative aeration where you're sort of forcing air up through or sucking it back out. But like that kind of works out okay. And then maybe that really is the cheapest option. From a greenhouse gas standpoint, if you can upgrade it to renewable natural gas, that's pretty good. Especially if you can offset diesel, but even if you offset natural gas, if you inject it into a pipeline, that looks good. It's generally preferable to electricity generation. Okay, credits for compost, it's all sort of like, you know, we're giving it credit for avoided fertilizer use on the field, but are farmers actually applying less fertilizer when they use compost? Sort of unclear. It becomes more of a like behavioral issue. Okay, but then we did the air pollutant emissions, and we put everything into social cost values. And this is where we were like, uh-oh, did we make like a units conversion error somewhere? But basically what we learned is this. Ammonia emissions from composting are like really pretty high. It's not so much the case for yard waste, but it is definitely the case when you start composting food waste that's got a lot of protein and stuff in it. It has a lot of sources of nitrogen. And since then we have done like extensive reviews on these emissions. We have confirmed that like, yeah, the measurements that our team took at the composting operation in Gilroy, that largely aligns with what other folks have published on the ammonia emissions from composting food waste, or waste that is primarily sort of food. And so this is a real problem for any plan that relies heavily on composting. Yeah?
Is ammonia toxic to?
Ammonia is a precursor to, so all these social cost values are based on fine particulate matter, PM 2.5. And so basically, what it does is reacts with SOx and NOx to form secondary PM in the atmosphere. And so the degree to which this happens does depend on whether the local atmosphere is ammonia limited. So if ammonia is like not the limiting reactant, like if you're in a place where there's already a lot of ammonia, then like adding more ammonia like may not drive this. And so there's definitely some like uncertainty in terms of the like reduced order models that we rely on. It is possible that it overestimates the social costs in some regions. And that may be especially true in California. So that's a caveat that I will add. But it is interesting that everybody I have talked to seems to be kind of coming to this realization that like ammonia emissions from composting are pretty substantial. There are ways to mitigate them, but yeah, like it's a real concern. So we did do this review, and this was funded by CARB to underpin some of their assumptions in the LCFS related to like what the emissions are for composting, both like just regular like food waste and then like post anaerobic digestion, like solid digestate. So we looked at like all of the measurements we could possibly get our hands on. And included, this was like my modeling person, Sarah Nordahl, but also Chelsea Preble, who did all the measurements. And so she kind of knows where all the bodies are buried when it comes to like what measurements are good and which ones are bad, which is something I'm not very good at knowing. So the ranges are big, but we confirmed that ammonia emissions really are a concern. And it's a concern for manure, and it's a concern for food waste. Greenhouse gas emissions, you know, the methane, like compost is pretty good from a greenhouse gas standpoint. We did confirm, like, the unfortunate part is aerating the compost and keeping it sort of turned, aerated, making sure that it doesn't have like little pockets that go anaerobic is really useful for reducing greenhouse gas emissions because it makes sure that you aren't emitting a lot of methane. The problem is that those things all tend to increase ammonia emissions. So, and the things you would do to then deal with the ammonia emissions are largely going to sort of like add costs. So what we're doing now is trying to take stock of all the organic waste across the US. My postdoc, Brendan Harrison, is doing this. And figure out, we're starting with composting. We want to know, like, if you wanted to do something sort of SB 1383 like across the whole country, what would that look like? How much compost would you generate? What are the costs and benefits from like a greenhouse gas and air pollution standpoint? And then how much farmland would have access to that compost? And we are trying to get a better handle on like the benefits of compost application, because that's something that we really didn't capture well in our original study. But I think it is a big need going forward. We've been working with Cal Recycle to make sure that we understand how the state did their cost-benefit analysis for scaling up composting, because you need to build a lot of new facilities for that. And the ammonia emissions, I would say the calculations that they have done would benefit from refinement. But there's some really smart people thinking all about this. So with that, I think I'm going to just pause and see if anybody has more substantive questions before we go to any other vignettes. Yeah?
I was going to ask, I feel like you could make the argument, like, because ammonia is like a localized, like, okay, compared to, if you have to like choose between methane and ammonia, could you make the argument that if your site is like isolated enough, because methane is a potent greenhouse gas, but ammonia, actually, is ammonia a greenhouse gas?
Not really, no.
Okay, so it's just like a local concern. Could you make the argument if your site is isolated enough that it's better to choose a local pollutant so you're not increasing greenhouse gas emissions?
Yeah, so that's why you can do these social cost calculations, and a tool like InMap or AP or easier from CMU, I guess 2 of them are CMU tools now, will give you location-specific monetized damages. And so it will take into account the population density and like where that PM would be formed. So you're right, like if it's in the middle of nowhere and there's nobody to breathe in those particles, like maybe it doesn't matter so much. One of the things that we're kind of sweating right now, to be honest with you, is like how to then factor in the notion of like disadvantaged communities and environmental justice. So you can say, well, there's not a lot of people there total, but the people who do live there have been like disproportionately burdened. There are areas like I was just in Merced not that long ago, and they have dealt with a lot from like the manure industry, like the odor, the flies, the air quality concerns, including ammonia, but definitely not limited to that. You know, it's a real problem. And in some of these communities, like in addition to, you know, some of them bearing more historical burden than others, there's also like a difference in their ability to cope. So like an example that my postdoc gave me, because he used to live down there before he moved to Berkeley, is that like if you have air conditioning, you can close your windows at night. And if you don't have air conditioning because you're in a rental or you own your place but you can't afford to, you know, install it or whatever, you open up your windows and you have to deal with all of the like environmental bads of whatever you're living next to. And so we are struggling with how best to like represent that in our analysis. I mean, one of the things that we can do and are doing now is like run scenarios where you say, well, you know, if we did all of this new development for like organic waste management and we avoided disadvantaged communities, like that's like a very coarse sort of crude metric to just take like the DOE's classification and just say like, well, don't build anything there. Like how different would it be? But you can run that kind of analysis. It's a challenge. But yeah, I mean, one way to look at it is you just sort of try to get the like just cost benefit analysis, take into account the fact that you want to build things where there aren't a lot of people. ZWED had all kinds of issues with odor complaints. They theorized that there were local residents who just hated the fact that the facility existed at all. And so they would have a phone tree, and if anybody smelled the facility, they would activate their phone tree, and then everyone would call in a complaint. And so, like especially at night in like limited mixing times, you end up with this weird situation where like one little strip of people will smell it, but like go a block over and they can't smell it because you have sort of like laminar flow. But they got a surprising amount of complaints for a while. They also ironically got a lot of complaints from the employees of the wastewater treatment plant next door. And you're like, come on, it could be you.
It's gonna be pretty bad to make them complain.
Yeah, I don't know. I mean, it was bad. I'll be honest, like I was pregnant at the time, so I was extra sensitive to smells, and the first time we were all just like, don't vomit, don't vomit. Any other questions before I move on? Yeah?
I was hoping to see hydrogen production through biomass somewhere.
Oh, yeah. Good point. We don't do a lot of hydrogen work in my group specifically, but as you note, there's a couple of ways that can work. The one with like existing technologies, right, is do RNG and then use steam methane reforming and make hydrogen that way. And that is very much like front of mind for regulators who are trying to like sort this out in the context of like hydrogen tax credits, for example. So you can go look at all of the comments about like how this should or shouldn't work, especially for RNG that comes from manure digesters that get like a very big methane offset credit. The other way you do it is gasification of like biomass, and then use the hydrogen from the syngas. That is super attractive for CDR people, and at least like on paper, like it looks pretty good. So if you go to the Roads to Removal report, which is one we put out in December 2023 with Livermore and a bunch of other partners. I mean, it was like a huge team effort, but like Livermore led it, and I led a chapter. That one looks like it has the largest potential. There are things that are cheaper, but that one is the cheapest one that has like a very big potential if you can do it for like all these different kinds of biomass. And then I think the devil's in the detail and like whether that actually, how well it works. These gasifiers are like hard to design and maintain, especially if you're sourcing heterogeneous biomass. But it's a great way to get like, you just get hydrogen out, so if you have a market for that, awesome. And then you have all this CO2 and you can just do geologic sequestration. But yeah.
Do you think the methane data has been emitted from that San Jose plant? We could produce some scalable amount of hydrogen from there?
Well, I mean, you could do, like, if they upgraded their biogas to RNG, then you could do SMR with that. The scale of that facility is almost certainly way too small to support an SMR plant. And so they would probably need to like pipe it to somewhere else. That is also a point of ongoing debate about like booking claim systems for RNG, sending those things to SMR facilities that might be like doing natural gas, and then they could take in some RNG. But yeah, like basically, yes, but probably not on site. Other questions? I saw another hand, but yeah.
But like, is this composting step a necessary step? Like, can you just, you know, put it into an anaerobic digester and, I don't know. I
Just
guess
land
at
apply the
that point,
digestate, right?
basically landfill it, but you've done something to it. Is that something?
Yeah, so here's the deal with the solid digestate, because this is a good point about the composting step. Digestate is less stable than composted material. And the state of California has restrictions on when you are allowed to land apply digestate. So during the rainy season, you cannot. And so, and there may be some like asterisks there in terms of localities. I'm not totally sure like what regulator is in charge of that. If it's like the water board and if it's like location specific. But I know there have been facilities in Southern California who have during the rainy season trucked their digestate across state lines to land apply them elsewhere where there are no such restrictions. And then you just land apply it during the times that you can in California. This was also why facilities would send their solid digestate to alternative daily cover at landfills. So that's the idea, is like just something that's kind of soil or soil-like to cover up the waste at the end of the day. And it's supposed to like reduce like rodents, flies, just make it like less gross. But if it's effectively landfilled, like then more waste gets put on top of it. It's landfilled. It's not going anywhere else. And California has said, whoa, that's not landfill diversion. You're still like landfilling your waste. So they don't want people to do that anymore. If you started with food waste, they say like, well, if that's just like a backdoor way to landfill food waste. But it makes life tricky because then they need to send their stuff to composters. Now in the cost-benefit analysis for SB 1383, what the state has done right now is assume that the ammonia emissions from landfilling waste are exactly the same as the ammonia emissions from composting the waste, which I'll refrain from commenting further on that. Any other questions? Yeah.
I'm wondering how you and your team approach communicating LCA findings with policymakers. I know you have a lot of partnerships with state agencies and such, but like, I don't know if you have things to share about that, and or if there's an example of the LCA findings influencing a policy decision or like an incentive plan.
Yeah. So, I mean, the good news is like California and at the federal level, we're engaged in both. There are people who are like very steeped in this stuff. Like you aren't, it's funny when we talk to, sometimes we'll seek like expert feedback on things like in my job with DOE right now. And when they come to the meeting, like they start at such a basic level and they're kind of telling us all stuff we already know. And I'm like, oh, so funny. I'm sure I did that. Like I probably rolled in being like, I'm the expert. You haven't thought about any of this stuff. And then I just rattle off a bunch of stuff that they've been like spending like many hours thinking about. So like, I would say like, we should definitely give those regulars credit. They're like really smart. And sometimes they can't tell you everything that they're doing, and so that comes across like maybe they haven't thought about it, but actually they've been like doing a ton. So that's one thing I've learned. But you know, it comes in different ways, right? Like in the low carbon fuel standard, obviously like that whole thing is LCA. So like they think about this all the time, and we can get straight into the weeds. Like if they come to us with a question, it's a very specific question. And it might be like in that composting emission study, then it's just a matter of like doing the literature, because we were like, yeah, you're right. The values are all over the place. Nobody's done like a systematic review or like a meta-analysis. We'll you know, and they funded us to do that. So that's, you know, for CARB and LCFS, that's kind of the level at which we engage. In other cases, there are parts of these agencies that are not as like steeped in the methods, but are also sort of trying to do it, and for one reason or another, they're not coordinating with the agencies that are better at doing it. So like, not to throw anybody under the bus here, but like CPUC, for example, they have biomethane procurement targets, and they want to somehow incorporate greenhouse gas emissions modeling into this, but they're kind of like, I guess they're just gonna like build their own thing, or maybe they already did. You're sort of like, oh, okay. And in that case, you have to start at a different place and maybe ask some questions about like, what are your goals here? Like, and maybe give them some resources they can draw on. And in other cases, you have to be a little careful because you may be critiquing things that are pretty locked in. Cost-benefit analysis for the organic waste diversion, right? Like, you sort of dig into the details and you ask some questions, and then you're like, all right, we're going to keep this conversation going, and we value you as partners, but we may also publish a paper that says like something different than what you have built into your stuff that you can't change now. So it kind of, yeah, I think in general, like they're really, really smart, and we always try, it's kind of our obligation to help them, right? Like we are UC employees. Even though state funding ebbs and flows, like we should bring value to the state. They've got access to all of these wonderful experts, and we kind of approach it as like, how can I help you? Even if you're not gonna pay us any money, like I still wanna give you what you need, because they have a hard job. They have a really hard job. Any other questions? All right. We're getting pretty low on time here, so I don't know if I'm going to do like a whole another like deep dive here. But why don't we talk a little bit about integration with geologic sequestration? One of the things that you guys may not be aware of, but for some of you it might be useful, is in this roadster removal report that just came out. First of all, highly encourage you, like roads, then the #2 removal.org. There's a bunch of like data sets there that you can download, and I feel like people have not yet like fully appreciated the wealth of data that is available from that report. And some of it is awesome. So one of the things I personally really like is the geologic storage with injection costs, which I have never seen before. So this is cost per ton of CO2, and it's location specific. It's for like a fixed size. But when we started looking at like CDR potential and its alignment with, existing biorefineries that might have a CO2 stream, or like even facilities that could do post-combustion CO2 capture, this was super helpful to have. It came from Sue Havorka's group. She's at UT Austin, I believe, and is like deep into, she's a geologic sequestration expert, way more so than I ever will be. And so you can get these shape files and then figure out like what is the potential to integrate geologic CO2 storage into any of my decarbonization scenarios. That has been great. One of the things we've been working on geologic storage and like how to integrate that better into some of our like scenarios. And one of the things that I have come to appreciate is just how expensive it probably will be to do post-combustion geologic, like CO2 capture. So when you use these solvents to capture the CO2, they will react with pollutants that are in your stream. So I went into this study thinking like that there might be like co-benefits to CO2 capture because like the pollutants would get like caught up in the solvent, and so like maybe you'd be able to have like less particulate matter or something, and it would just get stuck in the solvent and it wouldn't like make it out into the atmosphere. And what I learned is that's actually a huge problem for the system, and you have to install a bunch of emissions control equipment up front before you do the CO2 capture. And so if anything, the benefit would be that it would force these facilities to install emissions controls equipment that they wouldn't do otherwise, because it's the only way to make the system work. Otherwise, you have really high solvent losses, and that's super expensive. But it has also sort of hit home the point for me that probably the low-hanging fruit for geologic CO2 storage is like going after any streams that are not post-combustion. So I am much more pessimistic about doing this at existing power plants and much more focused on like CO2 streams that are relatively pure as being kind of where you would start. And so it may be that CCS as a method for like greenhouse gas mitigation has a more limited potential than we are currently assuming when you factor in all the costs. And it may raise the bar for what we have to do with carbon removal. I don't know. I'm not sure how it's going to pencil out with like direct air capture versus like bolting on these CCS systems, but that's sort of my impression now after a few years. Yeah.
After the carbon capture storage takes place, are there plans on using this stored CO2, or are we just going to keep putting tanks in the ground and leaving them there? Like, are there like ideas or thoughts or anything being done, like maybe doing like carbon reduction or like CO2 reduction, maybe?
So, yeah, I mean, the first point to make is that the good news is you don't have to build tanks underground. You're usually injecting this into like pore space in rocks. And so ultimately this should be, like mineralization will get it in a stable form. That's sort of the long-term game there. And so people feel pretty confident about the durability of that storage, although there was a recent example, I think it was an ADM facility that had some groundwater contamination issues. That's largely what EPA is concerned about with these geologic storage projects. And so there's almost certainly some kinks to be worked out, although people would argue that that was an instance where like notifications happened early, they like developed a plan to mitigate the problem. But yeah, like geologic storage certainly has, lots of people feel very strongly negatively about this. CO2 utilization, so it's interesting, in the Inflation Reduction Act, there is a tax credit called 45Q to support CCS. And they pay more for geologic injection and storage than they do for CO2 utilization. So the push is really more for geologic storage. I think CO2 utilization, it kind of gets back to this, like, what are you turning it into? And I think it's really only useful if you're getting enough value. Like, I mean, that CO2 may not be sequestered necessarily. And so, yeah, it's sort of a circular carbon economy. Like, that sounds really awesome. But that only is beneficial if it like makes economic sense and like the emissions sort of pencil out in the end. But it's definitely not a way to get like CDR happening at any kind of meaningful scale. Anything you're going to turn CO2 in is probably going to be into is probably a small market unless e-fuels become like way more profitable than they look right now. There were a few other questions. Do those people still have hands? Yeah, geologic storage is the, we like went and did this roads removal report, and then we had like our first like rollout meeting at UC Merced. And I was totally unprepared for the community response. They invited like a bunch of farmers and stuff. Like it was not just like university professors and grad students and stuff. And when we got to the part about like CO2 pipelines and CO2 injection, people were getting up and shouting. They absolutely hated it. They were terrified of CO2 pipelines because, of course, CO2 is heavier than air. So, like, you know, if you have a rupture, like it settles on the ground, and so that's scary. You know, you don't want people to asphyxiate. But I have come away from that whole process feeling like, oh, it's probably not going to work if you have to build big, long CO2 pipelines. If I had to do a decarbonization scenario right now, I would take out all the CO2 pipelines. sorry, Jesse Jenkins. But like my net zero America version probably wouldn't have any CO2 pipelines after I went to that meeting. Yeah, it's you know, we'll be lucky if the permitting moves along for these like class 6 wells. We could do CO2 injection, but I think like it will be an uphill battle to build big, long-distance CO2 pipelines. Maybe in some rural areas, but if you go near densely populated areas, it's going to be a struggle. And I think even in the rural areas, you see a lot. I would be shocked if we got anything like that built in California. Yeah.
Just curious, does this map, do you know if it includes active, you know, fossil fuel extraction sites? Because I know, you know, some of the experts have been saying that, you know, enabling CO2 injection in geologic storage is just enabling further fossil fuel production by, you know, essentially maintaining fossil fuel companies from bringing them to the table because they're so good at it. So it's like they have to be the ones to build these geologic sites.
Well,
How, you know, I guess like, yeah, like, does this map include that? Is it like, no, these are empty geologic, you know, basins that can, you know, are being utilized?
So I think the primary place where that concern comes up is with enhanced oil recovery, like CO2 injection. And, you know, it's a valid argument. I'm trying to remember if 45Q pays anything for use of CO2 in EOR. I'd have to double check that. I don't really work on that one. But CARB, technically, somebody could take credit for the use of their CO2 in EOR in a pathway. However, their requirements for like the monitoring and like assurance of like durability of that storage that it stays down there are apparently so onerous that nobody has ever successfully taken credit for this. So, I mean, yeah, I think like people, what I have learned about some of these issues that are like a little sticky and you're like, well, technically it's going underground, but we also feel sort of icky about it, is like the reaction from policymakers when they cannot figure out how to like make a definitive decision or they can't justify it legally is to throw up a lot of administrative barriers to make it like technically possible, but in practice impossible. So if you ever see instances like that and you're like, this is so confusing, like why is it like that? You're like, it might be by design.